You can hear me, right? Good afternoon, everyone. So I'm going to talk about public key infrastructure, and I'm Maduranga Siriwardena. So to better understand this topic, we'll need a little background knowledge about cryptography. So I'll take a couple of minutes to explain what this means. If we go back in history, in ancient times, military leaders, so the kings needed mechanisms to communicate sensitive information without seen by the enemies. One such evidence we have about such a mechanism is the Caesar's cipher. I'll explain how this works in a later slide. And after some time, there were mechanisms implemented to break these kind of primitive encryption algorithms. If we come to the modern, like the recent history, the events like the invention of Diffie-Hellman key exchange, RSA algorithm, or the SSL protocol, and the standardization of post-quantum cryptography algorithms are like key events in the cryptography. Now let's see few core concepts of cryptography. First, we have the encryption and decryption. Encryption is basically scrambling data into secret code that only a holder of a secret key can read. So we have two main types of encryption, symmetric and asymmetric. I'll go through them in a later slide. And next, we have the concept called digital signatures. It's an electronic stamp that will let us verify the authenticity and the integrity of digital documents or messages. Symmetric encryption is an encryption mechanism that will use a single key to encrypt and decrypt. This method of encryption is faster than the other encryption mechanism I'm going to explain later. It has a main drawback that it requires a key to be shared, secret key to be shared between the message receiver and the sender. So I have mentioned two well-known encryption algorithms here. So I'll explain how the symmetric encryption works with the very basic example, Caesar's cipher. Caesar's cipher defines a shift key, which will shift the letters in a message. So if we take shift key as 3, it will shift the letters in the message by 3 letters. So A will become D, B will become E, and so on. So I have shown how the hello message will be encrypted here. And when you want to decrypt the message, you get the same shift key, and you do the reverse. So I have mentioned how the decryption works. So this is the very basic example. The example algorithms shown in the previous slide are far more complex. Of course, this algorithm can be brute forced, but because we have only 26 letters, and shift key can be only 26. So if you try 26 times, it can be brute forced. But there was a different problem as well. So though you make the message unreadable, you still have the frequency statistics of the data preserved in the encrypted message as well. So if you have a large enough message and you do a frequency analysis, you can see the patterns and break the message in that way as well. So the next type of encryption is asymmetric encryption. It uses a pair of keys instead of a single key for the encryption and decryption. There is a public key, which is a publicly exposed detail that is used for the encryption. And you have a private key, which should be kept private for the message decryption. If you consider the message sign-in flow, it happens the other way around. You sign the message using the private key, and you verify the signature using the public key. So this asymmetric encryption works on the concept called one-way trapdoor functions. These are like few well-known such functions and implementations of asymmetric encryption algorithms mentioned here. So I'll explain example for asymmetric encryption using the RSA algorithm, which is based on the prime factorization problem. So I'll be taking a small example to explain this. So in this algorithm, you take two large enough prime numbers, but for the demonstration purposes, I'll be taking two small numbers. So I have selected 3 and 11 as the two prime numbers I'm going to use. Then I take the multiplication of that, which is going to be 33. Then I calculate another number. That's multiplication of 1 less than each prime number I selected, which is going to be 20. Then I calculate another number that is co-prime to this number 20, which I have selected as number 3. So which means these 3 and 20 don't have any common factors. Then I select another number when it is multiplied by that co-prime number and take the mod operator 20, it's equal to 1. So I have selected 7 as that number. Now I have done all the calculations I need to define my keys. So I take 3, which was that co-prime number, and the 33, which was the multiplication, as the public key. And I take the 7, which was the last calculated number I got, and the multiplication 33 as the private key. So this RSA algorithm assumes that when you have number 33, it's hard to calculate the prime factors 3 and 11 for the large enough prime numbers with the available computing resources and the mathematical knowledge. So to encrypt the message, if I take 4 as the message I want to encrypt, I take 4 to the power of 3, that co-prime number, and take the mod operator 33, which was the multiplication. So the value is equal to 31, which is the encrypted message I'm going to get. So I send this message 31 to the other entity, the message receiver, and the message receiver will take 31 to the power of 7 and take mod operator on 33, which will be equal to 4. So this is equal to my original message. So this is how the message encryption and message decryption are done. So there are 4 main usages of cryptography. First one is confidentiality, which will make sure that only the intended parties are reading the message, which is mainly done through message encryption. Next, we have authentication, which verifies the identity of the parties in the communication. This is mainly done through digital certificates. I'll explain what a digital certificate is in a later slide. And the third one is integrity, which makes sure that messages are not altered during transmission. This is also mainly done through digital signatures. And the final one I have is non-repudiation, which prevents parties from denying their actions. When you sign a message, you cannot deny that you didn't sign that message. So this is also achieved through digital signatures. So now we have the basic background knowledge. We need to talk about this topic, public key infrastructure. So I'm sure that almost everyone of you have seen these screens. So if you have tested our on-prem products, you should have seen this first screenshot I have used here. So this is coming due to the self-signed certificates our products are using out of the box. All these error messages have different meanings and causes, but all of them are related to our topic. And in the same time, I think at least some of you have tried to get a digital certificate for a website from a certificate authority. So this is also a related use case to our topic. So I have extracted this definition from Wikipedia. I'm not going to read it. So if you read it carefully, you will see certain concepts I have already discussed. So now let's see what this topic really means. So to understand, we have few core concepts, core components like certificate authority, registration authority, and the validation authority, and few core concepts like digital certificates, private and public keys, certificate revocation list, online certificate status protocol, certificate signing request. So, and I have this diagram explaining what happens in the public key infrastructure, but I'm going to come back into this later. So now let's go through each of these components and concepts and see what they really mean. First, we have certificate authority or CA. Certificate authority is the entity that is responsible for issuing, managing, and revoking digital certificates. Certificate authority is basically signing digital certificates with its private key. So there is a hierarchy of certificate authorities, and mainly two types of authorities. So first we have the root CA, which sits at the top level of the hierarchy. And it has its own private key, key pair, which is the public key of that key pair is trusted by major clients like the web browsers. And then we have the intermediate certificate authorities, which have a certificate that's signed by the root CA, and it's going to issue certificates to the end entities like websites or users. So I have the certificate of WSO2.com website used here. So WSO2.com website certificate is signed by the intermediate CA, and then in turn that intermediate certificate CA is signed by the root CA. So as long as the browser trusts the DigiCert root CA certificate, it's going to trust the WSO2.com certificate as well. So I have mentioned a few well-known certificate authorities like Let's Encrypt and DigiCert. Now, next core component is registration authority, or RA. Registration authority is responsible for verifying the identity of the certificate requester. So if you try to get a certificate for WSO2.com website, you need to prove that you own the WSO2.com domain. So you submit a certificate signing, you request a certificate in the form of certificate signing request, and registration authority will validate this signing request and make sure the identity of the requester is correct, and it will forward it to the certificate authority to issue the certificate. Next we have the validation authority, or VA. This is mainly responsible for handling the certificate revocations. So this is mainly done through using the certificate revocation list or the online certificate status protocol. I'll go through these two in a later slide. So the next concept we have is digital certificate. Digital certificate is an electronic document that binds an entity's public key to its identity. So if you remember when we discussed asymmetric key encryption, your public key is publicly available information, but to avoid anyone from forging a public key for your identity, you need a digital certificate, because it's a certificate authority is guaranteeing that your public key and your identity are bound together. So I have again used the WSO2.com website certificate here. So a digital certificate will contain the information like the public key of the entity, the subject details like the name, domain name, and the organization, and the certificate authority who issued this certificate, and the certificate serial number, expiry date, and the signature of the certificate authority. So the next concept is public and private keys. We already went through about this in previous slide. I'm not going to explain it again. Next we have certificate revocation list. Certificate revocation list is used by a certificate authority to communicate about a revoked certificate. So this is a list of certificates that the certificate authority has revoked. So there can be several reasons to revoke a certificate. It can be the private key can be compromised, or the certificate owner's details can be changed, the domain owner can be changed, and so on. There is a small problem with this protocol. It needs to communicate a list of certificates with the client, which might not be needed. This whole list might not be needed by the client, but just one certificate is needed. So this can be inefficient when we use it practically. So we have a different solution for this. So it's the Online Certificate Status Protocol, or CSP. So instead of communicating a list of certificates, the client can directly check the status of the certificate from the validation authority using the certificate serial number. So final concept I'm going to talk about is certificate signing request, or CSR. So this is used by an entity to submit a request to CA to obtain a digital certificate. So the CSR request contains details like the public key of the entity and the information about the entity, like the name, domain name, and the organization. So let's see how PKI works in practice. I have the same diagram I had before as well. So first, the entity will generate a key pair and will submit a CSR request to the registration authority, which will be validated by the registration authority, and upon validation, it will be forwarded to the certificate authority to issue the certificate. So now the certificate is issued to the initial entity, and if someone wants to send a message to sensitive message to this initial entity, they can get the public key of that entity and encrypt the message and send it to the entity. So now entity has the private key. It can use it to decrypt the message and get the sensitive message. So if you consider the message sign-in flow, it happens the other way around. So this entity wants to send a message that needs to be verified for its authenticity to this entity. So it will sign the message using the private key of this entity and will send it to the other recipient. So upon the receiving of this message, this other entity can take the public key from this entity's digital certificate and check the status of the certificate status and validate the signature to verify it's not altered or tampered with within the transmission. Finally, if this entity wants to revoke the certificate, it can do so by contacting the certificate authority, which will be reflected in the responses from validation authority. So one of the key usages of PKI, or public key infrastructure, is transport layer security, or TLS. So the initial versions of this protocol was called Secure Socket Layer, or SSL, which was initially developed by Netscape. But to denote that it's no longer associated with Netscape, the name was changed to Transport Layer Security, or TLS. During the TLS handshake, the client and the server communicate the details like the versions of the TLS protocol it's going to use, the cipher suits or the encryption algorithms it's going to use, and the client will be authenticating or the validating the identity of the server it's going to communicate. After these steps, it will be the entities will be sharing a key called session key, which is symmetric encryption key, which is going to be used to the secure communication after the handshake is completed. This session key exchange will be done using the asymmetric encryption to make sure that no one else is going to see this session key. So TLS is providing three main requirements. First one is it's making sure that unwanted parties are not seeing the messages, and it's making sure the two parties in the communication are who they claim to be, and it's making sure that messages are not altered or tampered within the transmission. So now let's see where we as WSO2 use public key infrastructure. These are some of the examples I have worked with. There can be plenty more. So the first one is secure web communication. Majority of our products, I would say all the products, are using secure web communication using HTTPS and TLS protocols. And we have assertion signing for JWTs and SAML assertions. And next one is the X509 authentication. We can configure our digital certificate in our web browser so that when we try to authenticate to a web application using the identity server, it can use this certificate as our credential. So this can be used as a option, authentication option in the multi-factor authentication. And the final usage I'm going to talk about is securing APIs with mutual TLS. In usual communication, a client is validating the server certificate to make sure that it's talking to the correct endpoint. In this case, this is happening the other way around. The server is validating the client's digital certificate to make sure that only the trusted clients can invoke the server endpoints. So this security aspect is especially important in the cases like the sensitive financial APIs. So finally, I'm going to talk about an important challenge for the cryptography and PKI, which is going to be quantum computing. So in 1990s, mathematician Peter Shaw has proved that classical encryption algorithms can be broken using quantum computers. But still, with the currently available quantum computers, this is not practically doable. But the problem is hackers can store encrypted sensitive data, and when there are powerful quantum computers are available, they can decrypt the encrypted messages and get this sensitive information. So because of this, post-quantum cryptographic algorithms has come into the picture, which cannot be broken by both classical and quantum computers. So I have mentioned two well-known post-quantum cryptographic algorithms, which are Kyber and dilithium. So that's what I was going to discuss. If you have any questions, please reach out to me. Thank you.